When they say the best things in life are free, I think they're probably referring to distributed element filters. What could be better than a little piece of copper on your circuit board instead of paying $20 or more for some custom filter? If you're not familiar with distributed element filters, a great place to start is Wikipedia. They actually have a great write-up on the subject, talking about open stubs, shorted stubs, etc., as well as some fancier types. So there already exist some pretty good tools. One of my favorites is Marquee Microwave. And if you need a narrow bandpass filter, I'd probably just go straight here. You can see here, a fifth order Chebyshev bandpass with an interdigital topology. It's just a click of a button away, and they even give you all of the measurements based on your dielectric constant and your dielectric height here. So yeah, great tool here if you don't know where to start or just want to see what's already out there. But I did decide to use some of my tokens for Claude Code and did some vibe coding last night and came up with this. This is the AI7SG Distributed Element Filter Designer. The way it works, you can load and save files. If we wanted to change an element, there's open shunts, shorted shunts, transmission lines, series inductors and capacitors, and one of my favorites, which is this step shunt here at the bottom. One thing that's nice about mine is it lets you kind of do arbitrary things, and you can actually set up some optimizer goals. What you want your pass band to be, what you want your stop band to be, and then when you click optimize, it will do its best to meet those goals. I have a couple examples. I have this band pass, and I also threw in a low pass filter. So you can play around with these, and depending on your filter requirements, play around with different transmission lines and open and shorted shunts. And you can always just hit calculate after you put some elements in and see what happens. And once you get close, you can click on this optimize button and it'll basically give you a score. Negative scores are passing, positive scores are failing. Not that it matters, it'll just make you a little plot here. Let's see, what else? If, let's say we wanted to change our goals and we really don't care about passband so much, maybe that could be half a dB, but we want a little bit better insertion loss, or a little better stop band. So we can do that and then re-optimize. And you can see it couldn't quite meet the goal. It was a positive number, but it came pretty close, and you could play around with these electrical lengths and your actual stop band range, and eventually you could get it to pass just fine. So if we wanted to, let's say, change our goal slightly and maybe allow a little bit larger transition region and something like this, and then re-optimize, and it still didn't want to pass. And re-optimize. And now it's passing. Anyway, yeah, you can play around. There's a lot to explore, and a lot of different filter types you can design. When it comes time to convert this to an actual filter, you'll probably want to go to, I like this WCalc tool. It's not perfect, but it gets you in the ballpark. Basically, your goal is going to be some trace widths and then some trace lengths, probably in mils, based on your frequency. I should also add that LT-Spice is capable of verifying any circuit that you develop. Use their transmission line. Let's see if you want. you want to place a T-line, transmission line, and basically if it's shorted, there's your shorted stub, and if you did not have a short here, that would act as an open stub. Now, one thing to be aware of when you're building distributed element filters is there is, especially on open stubs, there's going to be some fringe capacitance, and that fringe capacitance is going to make each stub act just a little bit longer than it actually is. So be aware of that. Look for some rules of thumb on the internet. It's usually just a fraction of your dielectric thickness that you have to subtract out. But once you do that, you should have something that matches simulations reasonably well. If you're wondering how the distributed element filters work, basically it all boils down to one equation. How impedance shifts as you rotate through a transmission line. Because if you think about what is an open stub, but a perfect open rotated through a transmission line, same as a shorted stub. What is a shorted stub but a perfect short rotated through a transmission line? And then all you really need is your series parallel impedance equations to put everything together. I will put a link to this software in the comments, and like and subscribe.